the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are going through linear independence topics right now. You should already be strongly familiar with all the previous topics in linear algebra. That would include row reduction methods and vector equations specifically. Also, homogeneous linear systems and matrix equations. If you don't know the definition of linear independence or linear dependence, it's probably a good idea to rewind a couple videos where I define those. What we're going to do in this video is basically expand what we were saying in previous videos. We were talking about in previous videos sets of one or two vectors. We're kind of keeping it small, but now we're going to grow our theory to include sets of more than two vectors. Even though the title says sets of two or more vectors, really, we're probably going to focus more on large sets of vectors. So here we are with this first theorem, and notice it is a numbered theorem. In the text that I use, that means that it is a very important theorem. And this theorem states the following: a set of two or more vectors is linearly dependent if and only if at least one of the vectors is a linear combination of the others. Now, to be honest with you, we just proved a theorem in the previous video that is very similar to this. It's this theorem right here. It's not a numbered theorem, but it was this theorem right here. Let me do some erasing. So the theorem that we proved in the previous video is really concerned with a set of two vectors, first of all. So we have to grow that theory now. But the way it was stated is this: a set of two vectors is linearly independent if and only if the vectors are not multiples of one another. And then I mentioned in that video that you can do the contrapositive of an if and only if, a bijection. The contrapositive of an if and only if, or actually maybe I should state it this way, an if and only if has this logic structure. P is true if and only if Q is true. But we know that every theorem that we're handed, its contrapositive is also a theorem that is true. Well, the contrapositive of a bijection like this is actually this guy right here. If not P is true, then not Q is true. And if not Q is true, then not P is true. So that's the contrapositive of a bijection. And so this bijection, original bijection, deals with a set of two vectors that is linearly independent, stating that that is true if and only if the vectors are not multiples of one another. Well, the contrapositive of that tells us a set of two vectors is linearly dependent if and only if the vectors are multiples of each other. And we actually proved that last time. So that being said, going back to what we're going to be working with in this video, you can see that this is exactly, or near to, I should say, that contrapositive statement. A set of two or more vectors, that's the only difference, the two or more vectors, is linearly dependent if and only if at least one of the vectors is a linear combination of the others. Suppose a set of vectors is linearly dependent. So we're starting the forward argument. Notice I listed out two or more vectors. So we're going to assume that P here is greater than or equal to 2. All right, that being said, then there must be scalars C1, C2, all the way to CP that are not all 0, such that the linear combination of those vectors using those weights becomes 0. And remember, at least one of those constants is non-zero. Little aside here, when I label or index my vectors, notice that I went v sub 1, v sub 2, all the way to v sub p. And you might be wondering why sometimes I use n as the final index or p as the final index. There is actually a reason why I choose to stop at an index other than n, mainly because n is associated with the size of a matrix, right? The number of columns of a matrix. However, I want to disassociate this conversation from matrices just for the time being. So I'm using just an arbitrary ending index, p. All right, now that that is out of the way, we want to show that at least one of the vectors is a linear combination of the others. Now let's throw out one possibility already. Since not all those constants are 0, let's go ahead and assume that c sub I is non-zero. Well, if that's the case, which it is, there's at least one of those weights that's non-zero, then what we can do is move c sub I, v sub I to the other side of this equation using subtraction. And it looks a little long-winded. It's only because I needed to set up a pattern there. So we have c1 v1 plus c2 v2. That sets the pattern that we're going by ones in the index, all the way up to c sub I minus 1, v sub I minus 1. And then all of a sudden we break the pattern because we're skipping over c sub I, v sub I. So the next element in that, or the next term in that list is c sub I plus 1, v sub I plus 1, plus c sub I plus 2, v sub I plus 2. So there goes the pattern again, increasing by 1, all the way until we get to c sub p, v sub p. Basically, that left-hand side is just missing c sub I, v sub I, and that's because we subtracted it from both sides. Now all I need to do is divide both sides by c sub I, a negative c sub I. And there you have it. This tells us that v sub I, that vector in that linearly dependent list of vectors, is actually a linear combination of all the other vectors in the set. The weights of that linear combination are listed as negative c1 over c sub I, negative c sub 2 over c sub I, and so on and so forth down the line. That actually proves the forward part. If two or more vectors are linearly dependent, then at least one of the vectors is a linear combination of the others. Now let's go backwards. So we're going to assume that at least one of the vectors is a linear combination of the others, and then use that to prove the set is linearly dependent. Now suppose that there is a vector in our list of vectors, and we're going to call that v sub I again, such that that vector is a linear combination of the others. Well then, that vector, v sub I, is just a linear combination of the other vectors, d1 v1 plus d2 v2, all the way up to dp vp, where v sub I is omitted from the summation on the right-hand side. That's just so that we know we're isolating v sub I, the vector. Notice the coefficient of v sub I is non-zero. It's actually a number 1. That's going to be important in a moment. Let's go ahead and move that to the other side of this equation. And we arrive at the following equation. 0 is equal to d sub 1 v sub 1 plus d sub 2 v sub 2. And that summation goes on until you get to that subtraction of v sub I somewhere in the middle. In fact, it probably would have been safer to have written that at the very end. Just like that. Just a little bit cleaner. Well, okay, now we have this linear combination of the vectors from our original set. It goes through all the vectors, v sub 1 all the way through v sub p. Even v sub I is there. Notice the coefficient of v sub I is non-zero. Thus, we now have a linear combination of our vectors where at least one of the weights is non-zero, and this linear combination becomes the zero vector. That means, by definition, those vectors are linearly dependent. And that finishes the proof. Very quick. Well, at least not too bad. So we've proved forwards that a set of two or more vectors being linearly dependent implies that at least one of the vectors is a linear combination of the others, and then we proved backwards that if one of them is a linear combination of the others, then the set is linearly dependent. Now we do have a visual of this that will really help out. This visual is for r cubed, but the idea is you have two vectors, u and v, and a third vector that's a linear combination of those two vectors u and v. Now by that theorem, if you have a set of three vectors, one of which is a linear combination of the other vectors, then that set is linearly dependent. And this set is linearly dependent visually because that blue vector is extraneous. There's no need to include that blue vector in a list of vectors that creates this space, which is a plane in R cubed. That space or plane in R cubed can be generated by linear combinations of just u and v. There's no need to include w because that is actually generated by a linear combination of u and v. And the language down here just means the span of u and v, which is the set of all linear combinations of u and v, includes w, because w is a linear combination of u and v. So there we go. That's a visual of a linearly dependent set of vectors in R cubed. The set of vectors that's linearly dependent is u, v, and w. And it's dependent because w is in the span of u and v. It is generated by u and v. So there's no need to have included w. Now, if you remove w from that list, then u and v visually are linearly independent. Again, if you could somehow remove that vector w, u and v are actually linearly independent because you cannot generate u just from the vector v and vice versa. The only thing, if I only handed you the vector u, the only stuff that you could create from that is multiples of it. So essentially it would be this line in R cubed that you could create with the vector u. You can never create this other vector v. All right, so let's take a look at a different visual. We're given three vectors, the same two vectors for u and v, by the way, but w is lifted up into a third dimension. So in the previous visual, w was on the same plane as u and v. But now when you slightly tilt it up to give an extra little dimension to that vector w, all of a sudden we can see it cannot be generated from u and v. U and v only generate that plane, that shaded plane in R cubed. So they cannot generate the vector w. So w is not in the span of u and v. That is, w is not a linear combination of u and v. So the set of vectors u, v, and w would be linearly independent. So that's a pretty decent visual of what's going on in that last theorem. Another thing that I would like to mention, however, is a little bit of a warning that confuses some students. Not a lot of students get befuddled by this, but every once in a while I do have some students that just think the following is true. So not all vectors in a linearly dependent set are actually combinations of the others. It only takes one bad apple, basically. So if I give you 10 vectors and I say that set of 10 vectors is linearly dependent, it doesn't mean that they all rely upon each other. It just means there might only be one bad apple. If you remove that bad apple, it may become a linearly independent set. This visual is kind of showing that. This set of three vectors is currently linearly dependent. However, it's linearly dependent because of one bad actor. If you remove this bad actor, all of a sudden, the set becomes linearly independent. And that's very important because, again, some people think, oh, linearly dependent sets, that means that every vector can be written in terms of other vectors. And that's not true. It's just not true. You can see right here, u cannot be written in terms of v. So it is not true that this linearly dependent set of three vectors requires that each vector is a linear combination of all the others. That's not true. So going back to the warning statement, not all vectors in a linearly dependent set are linear combinations of the others. It only takes one bad apple to be a linear combination and to ruin linear independence. And often what happens is that students will say, well, this vector is not a linear combination of the other vectors, so this set is linearly independent. And the fact is, proving linear independence or trying to prove linear independence by checking linear combinations is really hard, because you have to check through all vectors to see if any of them are linear combinations of others. And that's what this last sentence is. Thus, it is not enough to show that only one vector is not a linear combination of the others to say, oh, this is linearly independent. No, you have to, if you're trying to show linear independence that way, it's exhaustive. In other words, you have to go through and do it for every single vector in the set. It's just terrible. So let's try to use this theory here. Are the vectors v sub 1, which is negative 1, 0, 3, and v sub 2, 2, 0, 8, linearly independent? Describe the set spanned by these vectors or generated by these vectors, and then explain why a vector u is in the span of these two vectors if and only if the set u, v1, v2 is linearly dependent. Well, first of all, that last statement, explain why a vector u is in the span of those two vectors if and only if the set u, v sub 1, v sub 2 is linearly dependent. That's literally the theorem we just proved. If u is in the span of those two vectors, u is a linear combination of those two vectors. And that's what I've written here. However, according to the theorem we just proved, if at least one of the vectors is a linear combination of the others, then the set of those vectors is linearly dependent. So by theorem 7, the one that we just introduced and proved, the set of vectors u, v sub 1, v sub 2 is linearly dependent. So that kind of takes this off our list. And that is, by the way, an if and only if, that theorem. So now let's go ahead and determine, are these two specific vectors linearly independent? And I gave you a list in a previous video to help you determine the method you're going to use when proving linear independence or linear dependence. And that's this list here. Given a set of vectors, determine whether they are linearly independent. So the way that I will often do it is I'll just build a matrix and determine if the homogeneous matrix equation ax equals 0 has only the trivial solution. If it only has the trivial solution, the vectors are linearly independent. If it has more than the trivial solution, they're linearly dependent. So that's how I would recommend approaching this problem at hand. I build an augmented matrix where the columns are the vectors v sub 1 and v sub 2, at least the columns in the coefficient matrix. It's an augmented matrix to an homogeneous matrix equation. So not only did I take 3 times row 1 and add it to row 3 to become the new row 3, but then I swapped rows 2 and 3 here. But you can see that we have a pivot in column 1 and a pivot in column 2. So we have a pivot in both columns of the coefficient matrix, so there's not a free variable. And reaching back into our critical theorem list so far in linear algebra, we know that because this is a homogeneous linear system, it's always consistent. And we also know from this theorem 2 right here, if we have a consistent linear system and it has no free variables, which is the case we're dealing with, then the solution is unique. That is, not only do we have a homogeneous linear system that has 0 as its solution, but because we don't have any free variables, that solution is the only solution. So there are not any free variables, so by theorem 2, the solution to the related system must be unique. Hence, ax equals 0 only has the trivial solution because it has at least that solution, and it only has one solution, so it is the trivial solution. Thus, the columns of A are linearly independent. Notice that's a very rich statement. It's full of theory. So this is what happens in linear algebra. Every sentence that you're writing down is built from theory and definitions. So there's a lot of thinking involved when you write down something like this. There's a lot of learning that you're showcasing. So we've shown that those vectors, which are the columns of A in our augmented matrix, are linearly independent. Now all we need to do is describe the set spanned by these vectors. Well, the easiest way to note this is if you've had Calc 3. If you've had a semester in Calc 3, you know that these two vectors are in R cubed, or three-dimensional space. However, their second entry is always 0. So these two vectors span the x1, x3 plane. I could showcase that in a drawing, but I have to admit my drawings are always lackluster, but I'll try. Well, I have to say that's pretty good for me. So remember, the two vectors are -1, 0, 3 and 2, 0, 8. So this first vector v sub 1, I went backwards 1 in the x1 direction, nowhere in the x2 direction, and up 3 in the x3 direction, and then 2, 0, 8 for v sub 2. And that creates that plane in R cubed. And actually that plane goes down too. I just didn't draw that in. But it is a vertical plane. There you go. I'm not really going to draw the rest because it'll start messing with my perspective. And here is another theorem that is numbered in the text that I use. Very important theorem. If a set contains more vectors than the dimension of the vectors, then the set is linearly dependent. Now, I mentioned this in a previous video as part of a how-to. A set that contains too many vectors is likely to be linearly dependent. In fact, is always going to be linearly dependent. And we describe that as a short, wide matrix. We didn't really prove it at that time. We just gave a justification, but now we're actually going to prove that. And what's nice about this theorem, it's not an if and only if, so the proof only goes one direction. It's kind of very nice. So let's create a set of vectors that has more vectors than dimension of the vectors. So let v sub 1, v sub 2, all the way to v sub n. Now, because I'm using that index n, you probably know that I'm going to use a matrix in a moment. That's a set of vectors. In Rm, that means every vector has m entries, where n is greater than m. So maybe I should write this off to the side. If n is greater than m, then the number of vectors, n, must be greater than the dimension of each vector, m. In fact, I'll just write that down. There we go. That is, the number of vectors is greater than the number of entries in each vector. If we build a matrix from this, then the matrix, A in this case, is an m by n matrix. Again, it has more columns than it has rows. Well, if that's the case, then the matrix equation ax equals 0, the homogeneous equation, represents a system with more variables than rows. Well, if you have more variables than you have rows, then you're guaranteed to have a free variable. Now remember, that homogeneous equation has at least one solution, 0. So it's consistent. But we have a free variable, so now that we have a free variable, we know there are an infinite number of solutions, which tells us there's a non-trivial solution to the homogeneous equation. Again, I can guarantee that because we have a free variable. A free variable increases the number of solutions. We started with just the trivial, now we have more than just the trivial solution, so we have a non-trivial solution. Since it has a non-trivial solution, the columns of A, which are the vectors that we're interested in, are linearly dependent. And that's it. We started with that the set contains more vectors than dimensions of the vectors. That then implied through logical deductive argument that the set is linearly dependent. This is a very, very nice theorem to use. It's unfortunately not named, but it's a really nice theorem to use. We have finally arrived at the last theorem in this material. And this is a theorem that I had mentioned earlier in a previous video, that any set containing the zero vector is going to be linearly dependent. We're actually going to prove that now. So let's create a set of vectors that includes the zero vector. We're going to let v sub 0, v sub 1, all the way to v sub p be a set of vectors in Rm. I started at v sub 0 just because I wanted to index the 0th vector as the one that's the zero vector. So this is where v sub 0 is equal to 0. That's without loss of any generality. So in other words, it could be the case that v sub 10 is the zero vector. It doesn't really matter where that vector appears within the set. So without loss of generality, I'm just re-indexing it. If it was the 10th vector, I'm re-indexing it to be the 0th vector. Well then, 1 times v sub 0 plus 0 times each of the other vectors is going to be the zero vector. Notice the weights that we've chosen are not all 0. In fact, the very first weight is non-zero. So there's a collection of weights, not all of which are 0, that causes this linear combination to become the zero vector. By definition, that set of vectors must be linearly dependent. A really fast theorem to prove, a very nice theorem to have. It's not super common that you get to use it. However, when you can use it, it's pretty rad. All right, in summary, in the last few videos, here are the theorems that we've introduced. The columns of a matrix A are linearly independent if and only if the equation AX equals 0 has only the trivial solution. Remember, we have a contrapositive form of that. The columns of a matrix A are linearly dependent if and only if the equation AX equals 0 has more than just the trivial solution. Now I'm going to erase all my brand new ink there to get it back to its regular form. Another theorem we were introduced to. A set of only one vector is linearly independent if and only if the vector is not the zero vector. Not a super powerful theorem, but there it is. A set of two vectors is linearly independent if and only if the vectors are not multiples of one another. That's kind of a baby theorem leading up to a bigger theorem. And the bigger theorem is theorem 7. That is actually a more generalized statement than the one I just highlighted. So a set of two or more vectors is linearly dependent if and only if at least one of the vectors is a linear combination of the others. Theorem 8, if a set contains more vectors than the dimensions of each vector, then the set is linearly dependent. That is useful more often than you might think. And finally, theorem 9, any set containing the zero vector is linearly dependent. That one is less useful than you would think for a numbered theorem, but it does come up every once in a while. All right, that does it for linear independence. I hope these videos have helped you. If you wouldn't mind, give a like. I hear that does something. Subscribe if you want to. If not, that's cool. I hope you have a wonderful day. Be a pleasant human being on this planet.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.